Thank you very much, Philip, for your kind introduction. And yeah, good morning, gentlemen, and yeah, no ladies here. So for me, it's very happy, and also I'm very honored to give a presentation here. And thanks for the organization for bringing me here to this very amazing city here. So next.
Oh yeah.
Next one, no problem. So I think my talk in general will consist 4 parts. Like first part will be a brief introduction to the methods and also the motivation of my study here. So here we know actually I think most of us knows that additive manufacturing, so it's a kind of a new technology widely used in many different kind of industries, has also a lot of advantages such as high material utilization, short production cycles, and also so on. And now there's a bigger concern with the material made by AM, so it's a fatigue problem. Now in China, we want to use this material in aero engine or aerospace. So the fatigue problem is a big concern because it's difficult to predict crack initiation and fatigue lifetime. It's because in this material widely exist the crack and the shapes and the size, orientation of these cracks are very strange. And also the microstructure is anisotropic, and also there are some cracks, some Lego fusions, and this makes crack initiation very easy, and maybe multiple crack initiation also exists, so it's difficult. So it's a challenge task here, I think, in general, in fatigue regime. So the question raised that we want to, on one hand, the engineering is this application, is this technology, and on the other hand, it's difficult to predict. And also the microstructure also is very complicated, like this. They widely use the melting pool microstructure, anisotropic, like equal X grain size together with this laminar microstructure grain size, and also some kind of this say some cracks like the fusions, they coexist and have effect on dislocation movement, also has the effect on fatigue lifetime. So this shows that in high fatigue lifetime, which made by this material, you can see the scatter, the distribution of fatigue is big, is very large, so it's difficult to predict. So for engineering, also for scientific research, it's big concern. So this also, of course, there are also some other methods like crystal plasticity method and also phase field method, and also you can see the microstructure, but still it's not enough. We have to develop a framework which can predict lifetime accurately, precisely, and also fast. And here we try to link this machine learning method also together with crystal plasticity method together. So we try to bring this kind of work. And of course, some work already been done for this digital recognition, for link the processing parameter of the additive manufacturing to fatigue lifetime. But still, there's no such kind of link between microstructure, crystal plasticity, fatigue, distribution of fatigue lifetime. So I think this is the goal, this is the motivation. So on one hand, we want to propose this kind of framework to fast and also precise predict fatigue lifetime, and also the distribution of fatigue lifetime, the scatter, that means. On the other hand, we also want to use a crystal plasticity to consider the grain size, the pore, Lego fusion, this kind of method. So here we will try to use crystal plasticity and also together with machine learning method. So here the material here we use is a kind of a laser power bed fusion nickel-based silver alloy. So it's a kind of a very typical alloy, and it's manufactured by some this kind of parameters, and also we observe microstructures and Lego fusion and this kind of effects. And from fatigue test, we saw some we observed some phenomena. For instance, the microstructure, the isotopic microstructure, they will evolve. So they will change the size and the orientation. They change because of I would say the local stress, such as the compressive stress. And we can see here the microstructure, they are not uniform, and there are, I would say, some columnar, some equal axis structure. So this also makes us a very challenging task to predict. So also we see here from this observation, the crack initiation, propagation in the initial stage, multiple crack exists, and then the coalescence to one main crack leading to final crack. And especially in the short crack propagation stage here, we can see that the crack propagation rate does not always increasing with K. So there are some fluctuation due to microstructure, especially due to the very complex microstructure for these additive manufacturing materials. So this means very complicated, this problem, and also a lot of challenges here. And so we want to conquer, for instance, one of them. So we need to consider the microstructure here. I think this method already, we already know that crystal plasticity can consider the dislocation movement and consider the damage, plastic accumulation, and deformation. Plastic deformation is caused by slip, and also this framework is well established. And with this method, of course, we can do some analysis. For instance, we can get RVE, representative volume element. And with this RVE method, there are also many parameters in the versus step. We need to calculate these parameters using this tension curve predicted by experiment, also by this model, and also by experiment. Here, once the parameters are calibrated, so we can use it to predict fatigue lifetime. And in the first step, we predict the accumulated plastic strain here with the Lego fusion here method. And and then we can see out some kind of circles. The accumulated plastic strain is quite stable here. And we use this kind of fatigue indicator parameter to correlate plastic strain with fatigue lifetime. And we made the prediction using the method. Also, the results are compared with different experimental ones. And here it shows this kind of fatigue indicator parameter, which can correlate the results from crystal plasticity and also with the fatigue lifetime. This worked well, but still the question still are here. So it's very the efficiency is very low. We have to do the RVE crystal plasticity. It's very low. It takes a lot of time for such kind of case. And for this additive, for the microstructure of the material made by AM, so the complex microstructure is always there. We have to do a lot of times and to get a distribution of fatigue lifetime. So the question raised whether there's a way to link directly from microstructure, and we use crystal plastics as a proximity, as a kind of a middle tool, and then correlate together finally with fatigue lifetime or with the schedule of fatigue lifetime. So next we will try to solve this problem here. And in the first step, the microstructure here is a physical microstructure from our observation from EBSD or other observations. We need to transfer to digital microstructure. And of course, there are different kind of these methods here. And in general, this is the framework we are going to develop here. We generate the digital microstructure here, use machine learning method. And then we use the microstructure as an input for crystal plasticity analysis. And then we did the method altogether to build a machine learning method like a digital microstructure, crystal plasticity, and the fatigue lifetime prediction, schedule, fatigue lifetime distribution here. And we are going to build this kind of framework. With that, I think more or less I will end my talk. here. So now, in general, it's the details here. In the first step, we get the microstructure here from EBSD, from observations, and you can see here the microstructure are complex, and both equal X and columnar grains existed, and also high-angle grain boundary existed. And then we try to convert this microstructure to a digital microstructure here, and we use this method. Also, it's called grain boundary noise diffusion probability method, and it's kind of, and I think this method is well explained in the summer school by our colleague from Rome in the first morning. If you are here, you were here. I think already. I think the idea is to add noise and also remove noise from the first picture to the final, and then by repeat this process, we can find a parameter which can characterize this microstructure very well. And but of course, we have to do some efforts to find this parameter to characterize to introduce the noise. And here we change this method, and we use this loss function for between the real microstructure and the physical microstructure. Once this parameter is done, and then we can get the real microstructure. But still we need to assign grain boundary, because there are some redundant lines, a lot of lines, and also there are some algorithms to remove some redundant lines and to form the real grains. And once we have grains, and we have to assign grain orientation, because the crystal plasticity, we need the grain orientation. And here we use this method. Also, is a typical method, and we assign the orientation to each pixel. So it's a kind of vector, and with this vector we can get so the microstructure. So it's done with the grain boundary and grain size and also orientation. So with that, so we can do the simulation for crystal plasticity here. So here we show some microstructures, orientations, and the grain size here. And before that, we also need to confirm whether the microstructure we generated makes sense or not, reasonable, agree with the real micro or not. So we make a comparison between this microstructure generated by using the method mentioned or is here. And here we compare the distribution of the grain size, aspect ratio, and the circularity of the grain size. And from these figures, it shows some difference here. And of course, in general, the tendencies are good. But if we plot here the density distribution here as the two parameters here, I would say they agree quite well between these two microstructures. So this proves that the method we use to generate digital microstructure are good. We can rely on this method for crystal plasticity analysis. So for crystal plasticity method, so it's the same. I think it's a routine, and we use the parameter and do calculations, and we use fatigue indicator parameter to correlate the damage with fatigue lifetime. And here you can see the different kind of strain amplitudes and the stress here. And we found that fatigue lifetime increases with the circularity, also increases with aspect ratio of the grain size, and also decreasing with the grain size. So I think these observations are in agreement with the experimental ones. And then also we compare here the stress strain distribution between the one from real microstructure and also from the generated microstructure. Here, I would say in good agreement here. No big stress strain concentration here. And before the machine learning method and also some very routine work has to be done, such as some parameters have to be calibrated, like the epoch, batch size, and the learning method. And here we use also we do the work as all the machine learning work and we get these parameters, and then we correlate with crystal plasticity. We calculate a lot of calculations with different kind of digital microstructure, and here we can get the distribution of fatigue lifetime at the different strain amplitude here. And here we can see that when the stress strain amplitude is high, that means stress is high, the sketch of the fatigue lifetime becomes narrow. So I think this is reasonable, because when the stress is very high and the stress is dominant instead of microstructure, so the scatter band is low. If the stress is very low, and then both stress and also the microstructure will work on fatigue lifetime. So makes the scatter more complicated. It's larger. And of course, we also compare fatigue lifetime at the different stress ratios here. These observations are in good agreement with the experimental observations here. And another thing we need to consider is that here in our microstructure is equal X and columnar both existing. But if we may do some heat treatment, so out of that, maybe only equal grain size microstructure existed. So a question is raised whether this one has a higher fatigue lifetime. So that means demonstrate the heat treatment is very good for the in additive manufacturing. So in this sense, we compare fatigue lifetime with different microstructure here. And here for this one, we see some very obvious stress concentration here at the corner of grain size, grain and boundary, and also we saw the shear bands, slip lines, and which may lead to crack initiation. And then we use the same method, crystal plasticity analysis, and we do the fatigue lifetime, and we compare them. And to our surprise, actually, the fatigue lifetime of that both equal X and the columnar microstructure has a higher one. This is because this heterogeneous nitrotropic can have more ability to accommodate strain localization and leading to a stronger fatigue lifetime behavior. This is the one, and I think almost the last case is that I don't know whether you noticed or not. In the past, we did not introduce any crack, any pore, lateral fusion. And here we also introduce the pore in the microstructure. We observe whether the pore, in this case, the fatigue life will decrease in, or how much will it decrease, and we introduce here. And also we found some phenomena. And here in the interaction, there will be some interaction between the pore and the grain side, and will make the accumulated plastic strain increase very fast, very significantly, and reduce fatigue lifetime. And of course, if there's a pore or lateral fusions and the scatter band, the standard deviation of the fatigue lifetime will be very small. And in this case, we also observed that the scatter here becomes very small, because the strain accumulated strain is localized and make the crack initiation easy to predict in this case. And also we compare the fatigue lifetime with a pore or without a pore here. This red line shows the fatigue lifetime without a pore, without a pore. And here this lines, this several points shows the fatigue lifetime predict with a pore. And here we can clearly see that the fatigue lifetime will be decreased significantly if there are some this kind of pores, lateral fusions, and of course the interaction between pore and microstructure will decrease fatigue lifetime significantly here. So, and of course, we can also see some person correlation to demonstrate whether there are some correlations between the input parameters here. Shows some weak correlation here. I think this one should be the last one. So with this, we developed with this framework the digital microstructure, crystal plasticity, and the fatigue lifetime, and altogether, then we use this super wide machine learning method, such as the artificial neural method, supporting vector, and extreme gradient boosting method to correlate to build this framework. And we predict fatigue lifetime, compare with the experiment, the actual one, and shows I would say, in general, they are in good agreement with each other. So with that, I think I'm almost done. So this demonstrates what the work I've done here in the presentation here. So in general, we try to use some method to generate digital microstructure to generate the grain distribution, size, orientation, and then we use this microstructure as input for crystal plasticity, and we use this framework to predict particular lifetime, also for the schedule distribution of particular lifetime. With that, I think there are also some other conclusions. I will not read them. Some kind of that. With that, thank you very much.